Okay, thanks. Yeah, so I'm somewhat nostalgic because this is my probably second last day in KGRC. Like, if you are moving and I'm still here tomorrow, but after that I probably won't come back to Josephinum again. So we'll see. Yeah. Anyway, so I also do not exactly remember my title, but I'm really going to talk about silver forcing and P-points, so it must be something like that. And most of the things I'll be talking about are joint work with Osvaldo Guzman. Some of the things, depending on how far I get, some of the things are joint work with Jonathan Werner as well, but we'll see if I get that far. And yeah. Okay, so let me start with some simple definition. Like the goal is to make the talk mostly elementary or mostly simple. So like there are only a few things which, well, there is some forcing which you need to know, but there are a few things which are really necessary to know in advance. So sometimes I'll be talking about trivial stuff. So don't be worried that there is something else that's really trivial if you feel that it's trivial. Okay. So I'll first do a few definitions, and then I'll probably talk about what's the story behind it. So, okay, so if C is a set of infinite subset of omega, and generally I will be, like most of the sets I'll be talking about are subsets of omega. So if there is a set and you actually exactly do not know where it's coming from, it's some subset of omega. So if I have C some subsets of omega, and let's assume that it's centered. Then what is a pseudo-intersection? So we'll say that P is pseudo-intersection of the set C if for each, let's call it U, for each U in C, U is P is modulo finite subset of P. So it's the usual notion. Okay, U. So the usual notion of pseudo intersection. This denotes modulo finite, so up to finite error. And then it's easy to check. The diagonal argument shows you that if C is countable, then every such C has an infinite pseudo-intersection. Also, when I'll say pseudo-intersection, generally I will assume that it's infinite. So very often I'll say the pseudo-intersection, what I will in fact mean infinite pseudo-intersection. Should be clear from the context.
By centered, you mean finite intersection property?
Yes, so by centered, I mean whenever I take finite subset, I take the real intersection, this is an infinite set. And yeah, because otherwise, like if I had two disjoint sets here, then infinite pseudo intersections would not exist anymore, and I'm not really interested in that case. And okay, and also this is just some notation. So let's say that we are given some countable sequence of sets, so subsets of omega, and let's say that we are given some function f, function from omega to omega. Then I can, let's assume that these di's are centered, so this C is in fact such di's here. Then I will be looking at this special pseudo-intersection. So this is, let's say, pseudo-intersection via the function f. So let's say that this is just the, it's denoted as pf, and here inside the sequence. So this is just the intersection of di, one of these sets, union fi. So I'm just saying what is the error of the ith set. So this is such P. So this, let's say, pseudo intersection of di via f. This is what I mean. This is definitely a pseudo intersection. Like the ith set has finite error at most fi, and these pseudo intersections are sort of typical. So whenever there is some pseudo intersection of this set di, there is some function f such that the pseudo intersection is a subset of this pseudo intersection. So generally when we are checking whether things have large pseudo-intersection or all the pseudo-intersections are small or things like that, it's sufficient to check it only over like this special type of pseudo-intersection. Also, one simple observation: if I have two functions f, which is dominated by function g, then pf and are what's the relation? This one is what, smaller, bigger or smaller? Bigger. Yeah, bigger. So typically the argument which I'll be doing is saying that like some sequence of set has only small pseudo-intersections. So I will argue that I can actually check only the special type of pseudo-intersection, and moreover I won't check all of these. I think I can take, for example, just some dominating family of functions and check this for every function from my dominating family that this pseudo-intersection is small. So yeah. I mean, like there is nothing behind it. This is just basic notation. Okay, so what are p-points? So p-points are some ultrafilters on omega. So U is p-point. So it's ultrafilter on omega. And when I say ultrafilter, I do generally mean non-principal. In principle, ultrafilters are not very interesting, so it's not considered them. Which is the property that every countable subset of U has a pseudo-intersection, which is again an element of U. So for each C countable subset of U, now we can say there is function such that P, F, and C is again in U. So this is what is being a p-point. Okay. So this so this is what this talk is about p-points. And so p-points were originally introduced by Walter Rudin. This was, I think, 56. Yeah. And so he made the definition of p-points, and like what was his motivation? What was he looking at? So he was actually studying the checksum compactification of integers, or I can say just countable discrete sets, and he was answering the question whether this is homogeneous space or not. And so how did his argument go? So first he noticed that, one thing you noticed, that being a p-point is a topological notion. Let's not go into details. But being a p-point is a topological notion. So his proof was to, like, the structure was that he constructed an ultrafilter which is not a p-point. He constructed an ultrafilter which is a p-point. So this gave him two points in omega star in the checksum compactification of integers, which are just topologically different. So they cannot be possibly taken one to each other by an automorphism. So yeah, maybe let's just quickly see why there are ultrafilters which are no p-points. So this is just a simple observation. Just take any ultrafilter U, non-principal ultrafilter U, which is disjoint with the ideal fin cross fin. So what does it mean? So now we are not really looking at ultrafilter on omega, but an ultrafilter on omega cross omega. What is the fin cross fin ideal? So say set is an ideal fin cross fin if it is covered by finitely many columns plus area below graph of a function. So this is the ideal fin cross fin, or people call this fin cross fin. So what I'm saying, that we take an ultrafilter such that whenever we do this, then actually this set will be in the ultrafilter. And this such ultrafilter can never be a p-point. These ultrafilters always exist. Just take the dual filter to fin cross fin and extend it to an ultrafilter. This is an example of such ultrafilter. Why is this not a p-point? So you'll be looking at, like, set everything except of the first column, everything except of the second column, everything except of the third column. So this is our sequence, the i's. These are all in the ultrafilter, and whenever we take a pseudo-intersection, so being a pseudo-intersection means it has at most finite intersection with each column. So it is covered by a graph, it is below a graph of some function, which is not in the ideal for not in the ultrafilter for sure, because it's in the ideal. Yeah, so this is like, so this is the argument that there are ultrafilters which are not P-points. And yeah, so the other half of the proof of Rudin was that there are also ultrafilters which are P-points. And this is somewhat more problematic. So what did he prove? He proved that if continuum hypothesis holds true, then P-points exist. And the argument is just inductive construction of length omega-1. Since you are only on countable steps, you use the fact that countable things do have pseudo-intersections, and so there is nothing more to it. So this was the original result. This is where the motivation for P-points came in. Of course, the disadvantage of the proof is that it needs CH. So how do you deal with that? Well, you either improve your definition of P-point to something else, which just you can prove that it exists in ZFC, or you improve your proof that something implies existence of P-points. So for one end, I think Kuhnen defined semi-selective or weak P-points. He defined weak P-points as sort of weakening of this thing, and these are already things which do exist in ZFC, and they are topological notion, and this already proves the non-homogeneity of omega star, which of course was proven earlier by Pospisil, I think, and then and there are various results about this. This is not the direction we are interested in. We our story is about improving this proof. So this was in '56, and then this was like during the time this was being improved. So Booth, it was in the year I have here is 70, is that Martin axiom is sufficient. So again, no surprise. Then Jussi Ketonen in 76 improved is that you just need this piece of Martin's axiom. Dominating number is continuum. Again, you can construct P-points. And so far, like in this direction, this is probably the best thing there is so far. And there is like one more result to mention. So this is Moore, Hrušák, Jamonia. And this is 2004, and this is sort of different type of result, which is that diamond of R. So diamond of R, this is, let's say, something like reaping number is omega-1 plus some little bit of some combinatorics. So this is like sort of other type of result. It's like previously this is like Martin's axiom, or that things are large. This type of result is that if the reaping number is small and a little bit of combinatorics holds, then P-points do exist. And as far as I know, these are the best things there are. There isn't any like smart construction of a P-point which I would know about. So that was the positive result. And then at some point, this was sort of big deal, I guess, at that point. So that was allegedly in 1977, Schellach proved that consistently there are no P-points. So like these results cannot be improved like to ZFC results. So it's really consistent that that in ZFC you have a model which does not have any P-points. Okay, let me say just a little bit about the strategy of how this is done, because sort of the strategy is the one which we'll use later as well. Okay. So the strategy is, of course, do it by forcing. So to start with like CH or something, and to create some forcing extension which does not have any p-points. Yes.
Is Booth's argument like essentially the same as a CH construction, or is there something more going on?
I would imagine it's just straightforward. I mean, I don't remember it, but I would just do the obvious thing, and I believe it. I think it must work.
The obvious thing is the tower. The tower. Like
Yeah.
P.
Yeah. Right. Yeah. Yeah. So there is like. Okay. So what's the strategy to create this? So let's say that you are given an ultrafilter U, which perhaps is a p-point. So let's say it's a p-point. And so what Schiller did, he defined a forcing. Let's call it GU. It's some sort of Grigoriev thing, but let's not go into details here. So it's some forcing which takes this p-point as a parameter, and it prevents U to being extendable to a p-point in, let's say, any further extension. Of course, this is like the way I said it is impossible. If you collapse continuum to omega, then you can always extend. So what really we will be considered, or what is considered here, are all omega bounding extensions. How this is done? So the forcing GU, it introduces some sequence of sets. Let's call it DI. And so these will be sets in the generic extension, and these are sets independent with respect to the ultrafilter, which means that if you want U to be extended in an ultrafilter, you have to in particular decide about each of these DIs, whether you are putting it in the ultrafilter or out of the ultrafilter. So in order to extend U to ultrafilter, or hopefully to a p-point, or possibly to a p-point, you need to decide for each I whether you are putting in the ultrafilter DI or the complement of DI. And the DIs which are introduced have the property that no way you do it, no way you choose the selection. So let's call for each x function from omega to 2, which chooses whether you are adding the D or its complement, and for each f, which possibly controls this thing, you have that pseudo intersection of f of DIs. Let's put here x or xi. So for each, arrange it in such a way that for each x and for each f, when you are looking at this, there will be always some U in the ultrafilter, which means in the ground model, such that the intersection with U is already empty. It's forced to be empty. And if you like once this is arranged, then this already makes sure that this is not extendable to a p-point in the extension. Then when you argue that this fact remains in every larger forcing extension, like you need to consider x's and f's which are coming from these larger extensions. But on the other hand, as long as you have omega bounding extensions, which in particular GU is, then the functions f, in fact, it's sufficient to check them only from the ground model. And for the x, you can do sort of similar argument. And yeah, so this is the basic strategy for the proof which Schiller had. And then you just iterate this with countable support iteration of length omega 2. This gives you, and you make sure that you plug in every possible candidate for a p-point, or in other words, every possible trace of ultrafilter which could be the intermediate model. This will give you a model where D is omega 1 because it's omega bounding forcing, so in particular this does not apply, and there are no P. Like this type of strategy is the only way how you can achieve a model without P-points. Like there is not much else than that you can do. Yeah. On the other hand,
so you know you need P less than C, so you have to do something in keeping some family.
Yeah.
So it's tempting to use omega bounding forcing.
Yeah, exactly.
Preservation theorem for that.
Yeah, exactly. Yeah, so there is not much wiggle room there. Like you have to do something like that. Yeah, but this raises some question, or people were asking questions. So for example, if you do this thing, then like whatever you do, you always end up with a model where continuum is omega 2. Like you cannot get anything like that. So like, is it necessary that C equals omega 2, or can we say that C is not equal to omega 2? Can we just add it here? So this was not known until now. Or this is specifically a question of Michael Hrušák. So he was asking whether perhaps it's a theorem of ZFC that whenever you have a canonical model, then there are P-points in there. So I'll just comment. So they have some, like in this paper, they have some sort of definition of what a canonical model is. So loosely speaking, it's something which you can achieve from a model where CH holds with a countable separate iteration of length omega 2 via forcings which are definable. So in part, like, or another definition, another notion which you can take a different definition. Canonical model is something which has a name. So like Laver, Miller, Silver, Random, Cohen, which the definitions are not exactly the same. Like Cohen and Random are not exactly countable support iteration, but yeah, whatever. Basically, it's a quick.
Only countably bounding canonical models if they have to have a name.
Yeah, that's just countably many things you need to solve. Yes. Sorry?
So the point is to allow use the parameter U.
Yeah, exactly.
So it's not canonical.
Yeah. It's not definable. It's like definable in the sense that it's not you can have this notion of like Suslin-Poe set or Borel-Poe set, which is, and you'd say that the conditions are elements of a Polish space, and the relations are. You can play all these games, and then you can ask. Then the question, specifically the question of Michael Hrušák was, if you do this, perhaps it's true that there just must be P-points in the extension. So. And right. And also this is just like a model. This doesn't give you any. Yeah. So like the question would be: is there an axiom which gives you non-existence of P-points?
I understand the point of Hrušák's remark. I mean, who cares if it's definable? You do bookkeeping arguments.
I mean, okay. Let me comment a little bit more about this thing.
NA from a definable.
Okay, so basically, for most models you can just outright say, for most canonical models you can just outright say, now then we are saying the most as most named. You can just outright say that there are P-points, because if you are not omega bounding, then you always get to here. On the other hand, if you have a definable forcing which does not add reaping creoles, then diamond R will hold. So this is sort of important that for these definable forcings you have all these theorems and all these facts that if you use them you cannot get rid of these associated diamonds. So this is like one thing. So in particular, this tells you that if you have a definable model and perhaps you do not want P-points there, it has to be something which is bounding, and at the same time it adds reaping creoles or independent creoles or splitting creoles. Okay, splitting creoles and independent creoles, I use them as synonym. It's just the same
In
thing.
theory, it splits everything in the count model.
Everything infinite, yes. Yeah, yeah. I'll define it in a moment.
So, there are many. There are some theorems that say, with definable forcings, you can, I don't know, you cannot increase the splitting number, for example, or every nicely, let's say, CCC definable forcing has to essentially contain Cohen or random forcing or do something else. I mean, there are some dichotomy theorems for, at least for CCC. Right?
Yeah, yeah.
Definable,
So this is useful because
forcing.
if you're doing something definable,
Then you have
a quick
automatically a
answer.
preservation theorem,
Yeah.
or in this case, a negative.
Yeah.
Okay.
Yes.
Yeah. Yeah, or the last thing is like, do you have like some statement which you can say like MA or something which you can say, and this just outright implies that there are no p-points or things like that. Yeah. So what like?
So for example, the Moore-Hlushek, the ammonia, essentially one of their theorems is that when you do at one of these definable iterations, whether or not the diamond for a cardinal invariant holds in the extension is if and only if the invariant is small.
Yes, exactly.
So yeah.
Yeah. So what David said is that so I hear that I said diamond R is in particular that R is omega-1 and some small combinatorics, and the results of Moore-Hlushek ammonia are that if you are dealing with definable forcings and iterate definable forcings, then already, as long as you preserve this, then already this combinatorics come for free. So basically
And it's only if and only if, like if you
Yeah.
define those forcings and you will, then there's
Yeah.
no-
Of course, this is consequence of this. Okay. Okay, and yeah, and sort of like time permitting, we will see answers to all these things. That this is not necessary. There is a canonical model, namely the silver model. So if you iterate silver reals, you get here, and there is and we have the axiom is that okay, if cofinality of the null ideal is strictly smaller than covering of V0 ideal, I'll define it later. So then this statement already, like some cardinal inequality between cardinal invariants, talking about some ideals, already implies that there are no p-points.
You say the second line there is just false. Is that what you're going to tell?
Canonical models have p-points. Yes,
False.
that's false. Yes.
Oh, okay, good.
Yeah. I mean, it's sort of surprising, but yes. And yeah, I should finish the story about canonical models and no p-points. So basically, this diamond R and D equals C. This gives you it leaves you with two options: random and silver. And so these are the two things you should look at. And for a long time, people thought that they knew this for random. So there was this result published. Okay, first of all, somebody proved that if you if you start with a model of CH, first you add omega-1 many Cohen reals, and after that you add random reals, omega-2 many random reals, then there will be p-points. So this is like an example that at least consistently there are p-points in every random model, or there are p-points in the random model consistently, and it's not really clear to whom this should be attributed. Arnie Miller blames Ken Cunan, and he refuses. But David knows more. David actually investigated, and
Cunan claimed that it was Blas. Blas, of course, said he didn't have anything to do with it, and
Did it eventually get that time?
oh. Yeah. Anyway, nobody knows. So yeah, then later there was this paper which had a proof that like this is just a theorem that p-points do exist in random model. So for a long time people did believe that this is known, and then came Osvaldo, who actually was reading the paper and figured out it's just plainly wrong. So or most of the paper is correct. Just one key argument is just false. And existence of in general existence of p-points in the random model is unknown. And recently Landau actually proved that if you have, so assuming CH CH plus square omega 1. So if you assume this in the ground model, and then you add omega too many random reals, then there will be p-points. So already having a ground model such that the random model over this does not have p-points, this already would have some consistency strength. So, but whether it's just in terms of FC that there are p-points, that's.
Random, you mean now a countable split duration?
I know.
Random or side by side?
Side by side. Yeah. So here comes the ambiguity with the definition of what the canonical.
Okay, so in the Cohen model, yes. Square?
I don't know. I think you should ask other people about squares, not mine. Yeah, I don't know. Okay. Yeah, right. Okay, so
Well, if you're going to destroy square omega 1, then omega 2 had to be at least mono.
No, my question was, if you add omega 1 many coordinates to a model of CH, do you always have square?
You always have square.
No matter what happens. I mean, I'm asking, is this a generalization of the previous?
Yeah, I'm not really sure. I'm unfortunately not.
No.
Okay.
Square is still a square. If you're not changing cardinals, the square is.
But maybe there was no square.
Oh, you mean you create a square?
Can you create a square? The coordinates
Because it's CCC, so you can pull a generic square back to the ground model.
Yeah. Mm-hmm.
Oh, but you.
Because you just say, like, I mean, the points that are forced to be in every club, and then the, I'm not sure when
Okay, so this is for, let's say, afterwards, or we'll see. Okay. Yeah. Yeah, so what I will be talking about is how that silver forcing actually can be used in place of this thing. Okay, so I'll do a short overview of how one can argue that something is not a p-point. So this will be still somewhat general and not very difficult. So let's say that we are given an ultrafilter U. So how do we prove that it's not a p-point? So what we are supposed to do, we should find some sequence of sets, I, which is so some sets in the ultrafilter, and we need to show that for every f, for every function, and the function can, we don't have to do it for every f, but just for some for f's coming from some dominating family. What we need to show that Pf of D is not in U. This is just still the same stuff. Yeah. So so what's the actual strategy for showing this? So for each, so what we will do, or what will be strategy, that for every f, for this f, we will find a function a. So a is an increasing function from omega to omega. So think of it as finding an interval partition. So the function a tells you where the boundaries between the intervals are, such that for each I, ai is above fi, and then you can majorize this Pf of D can be majorized by looking just at at traces of these in intervals. So I'll write it. So this is majorized by the union of di intersection and the interval between ai plus 1 and ai. So this set, maybe we will, okay, let's give it a name. Let's call this in general EA of this sequence D. So this set is definitely a superset of this thing, right? Because AI, the point in AI, like the lower boundary of the interval is always above Fi. So the intersection which we are taking, so if something ends up in the intersection, it has to be in particular in this given interval it has to be in Di. So what we will in fact prove, so the strategy for proving that this is not in U is for this F, finding this A, and finding some set in the ultrafilter such that U intersection this EA. D is empty. This is sufficient, right? And I mean, there is nothing involved. These are just very simple things. Just the notation gets a bit ugly. And this is the general strategy that we will be using through the proof. So I'm just spelling it out so that later we are not confused when we get to the point where this is used. Okay. So this is like outline of the strategy. Yeah, at that point, let's finally see what this silver forcing is. So some people call this pre-cree silver. Nowadays, people call it just silver, and I will denote it PS. It's PS, it's pre-cree silver, and S is usually used just for socks. So let's call it this PS. So I will first do one definition which are not really used, but maybe it's sort of yeah, we'll see. Okay, so let's say that we are given two sets A, B, subsets of omega. Okay, maybe let's make it capital. Then what can we call an interval? So let's say that then interval A, B, those are just all the sets which are in between, right? So these are C's such that between B. So let's say that on we are working with reals or infinite subset of omega, and we are working with these intervals. And then what is the usual Cohen forcing? So Cohen forcing is that you have reals, you have the sort of other intervals there, and you just force with open intervals, non-empty open intervals, and you say that a stronger condition is an interval, a stronger condition is a smaller interval, generic real is intersection generic filter. Right? So now just, I mean, just you get is silver forcing. So it's like this sort of intervals, smaller interval, smaller condition, generic real is intersection of the reals in these intervals. So it's yeah, you can, yeah, some people call this donuts, and then and in particular I think this is this donut name is called when we are looking at this V0 ideal. So let me say what this V0 ideal is. So for
the difference is infinite. The difference between A and B.
I mean, oh yeah, you are right. Yeah, thanks. I guess you are right. Otherwise, it would not really make really sense. Yeah. So let's say this is. Yeah. Okay, let's say B minus A is infinite. Anyway, I won't really be using this definition. I'm using a different one. Yeah, but this, but now this is sort of clear what this V0 ideal should be. So when, like for Cohen forcing, we have this ideal of nowhere than set and the sigma ideal of meager sets. So now we can just do the, like we can use the same definition. So we say that a null set is the set such that whenever you take an interval, you have a smaller interval, still not empty, which is disjoint from the set. So these are the null sets. So this is a sigma ideal, and this some people call it donut ideal. Some people just denote it V0, and so let's call it the donut ideal, and let's denote this meager version, or this version of the meager ideal, the V0 ideal, and this is this V0. I think Jörg Brendle used this notation originally, so next week you should ask him.
Like S from Marchevsky.
Yeah. But you know, I think in Marchevsky this comes from originally this being denoted this Scharfesses, right? I think they originally used this.
Really?
I think they. Let's not go there. Yeah, so this is where this V0 comes from. And so let's do the definition which is more common and which we will be really working with, but it's just the same thing. So the condition in precrete silver or in silver are just partial functions from omega to 2. Such that which fulfill the property that they are very much not total. They are not total, meaning that the complement of domain. So let's call it codomain. COD. Codomain of P, which is just omega minus domain. Domain of P is infinite. And P is stronger than Q if P is bigger than Q. So just partial functions ordered by extension, and it's not difficult to see that this is just the same definition. And the generic real then is just the union of the generic filter. So this will be a total function from omega into 2. So it's a characteristic function of some subset of omega. I will not really be distinguishing between characteristic functions and subsets. I will be mostly identifying them. And yeah, the generic real I will usually call it R, like for the generic real for the silver forcing. Okay. Yeah, and just so this is the silver forcing, and I will be also working with countable support product of silver forcing. So if I write this, so this is some cardinal kappa. So this is the product of these forcings with countable support, which means that only at most countably many positions the condition actually says something. So yeah, usual thing. And now I will just claim something.
You're not iterating, so
I can do both. Yeah. I mean, this is the key for example, for BT for this. If I want to approach this, I can't iterate, right? So the point is that I can both iterate, I can take product. It works. Yeah. So. Both this like if I take this product or just the silver forcing, they are proper. I am not going to prove it, and there's nothing like extraordinary. And this might be originally due to Baumgartner. I'm not sure. Never mind. One.
XMA structure.
I'm not sure whether you can just for this you can just invoke axiom A, but if it's not axiom A, then you just do the same thing. And there is nothing unusual. Yeah, and also the same proof, it gives you that these things do have the Sachs property. So what is the Sachs property? So in general, like I will do the general definition. So forcing has Sachs property if. So let's P has Sachs property if whenever I take x, let's say it's a name for a function from omega to omega, and for every condition, there is a stronger condition, and there is a slalom or tunnel. I will probably just use these two notions like without distinguishing between them. So there is a tunnel, so this is a sequence of subsets xi. I is a finite subset of omega. And the tunnel is narrow, so always the width of xi is, let's say that it's at most or exactly I plus 1, such that the condition Q forces x goes through this slalom. Yeah. So we are given a name for a function, and we can find this slalom, which is not too wild, such that this condition Q will force that the function does something like this, goes through the slalom or through the tunnel. And both these things do have the Sachs property. So that will be one of the important things that we will use.
So like omega bounding, this is really a property of universes.
Yeah, you're right. Yeah. What Martin is saying, that we don't really need to use this forcing terminology. We can just say that one universe has Sachs property or some smaller universe if we can find this slalom such that every function goes through it. And this for what we are doing this for, almost always this is just, you can just use this property of universes. It's not really important. This sucks to use in this forcing context. And one thing to notice.
The size of the tunnel is a bit arbitrary, isn't it? Because I plus 1 is a bit. Sachs would give you 2 to the I, right? Normally. And it's equivalent, right?
Yeah.
But
okay. Yeah. So what?
You said 2 to the I wouldn't make any difference.
No.
Yeah. Function which is not 0.
Every finite to 1.
If you don't advance the size.
Yeah.
No, unbounded, right?
Unbounded, has to go to infinity.
Yeah, fine, yeah. I mean, not, yeah, finite to 1. Finite to 1 function. So yeah, the comment is that here the function, it's not important that this is I plus 1, we can choose any finite to 1 function, put it here, limit the size here, and it's still the same property. Of course, you don't have the equality. Okay. The Sachs property implies omega bounding. This is sort of apparent from this picture. The function cannot get above this maximum of these slaloms. So we are fine with this respect. So Sachs property is, and we will be using the Sachs property sort of heavily.
Your point is that random forcing doesn't have the Sachs property.
Yeah.
It is omega bounding.
Yeah.
So this is something special.
Yeah, for the construction which we are going to employ, we need it. Well, in fact, we need bounding and we need Leibler properties, so, without saying what that is. Okay, and yeah, so I guess this is the prior knowledge which we need about these forcings. So let's do one simple lemma which will be necessary. Let me fit the lemma here in this corner and so lemma. Yeah, I'm not sure what I want to keep, so I'm sure I want to keep the lemma for later. So let's. Okay, so let's say, suppose that G and additive notation is a group. Don't be afraid, there is not going to be any group theory. And the size of the group is at least bigger than n squared. So we have some integer n and we have a group which is larger than n squared. Then for each x subset of the group, which has size n, or at most n, there is an element in the group which shifts the set X away from itself. So X intersection X minus S, this notation is just the set of elements which are a result of shifting each element from X by S, is empty. So why is this? So this is just a simple lemma which we will need in the construction. Quick proof. So what's the size of the set? Just X minus X in the group, and I am using the additive notation. It's not important that it's a billion, or we don't care. So the set of size X minus X is at most n square, right? And if we take some S, which is, so this is not the whole group. So there is some S which is not in the group, which is in the group but not in this set. Of course this S works here, because what does it mean? Like S is not a difference of, like, it's not the difference of two elements in X, so if we shift X, we don't get into X here. Nothing. So you should not, it's not nothing more there. But it will prove, this will be actually exactly what we need, and we will, if I manage to talk about some things, then yeah, we'll see. Okay. Yeah, right. So also to address these things. So I said that that if we want to have any chance for this to work, we definitely need the forcing to add splitting creoles. Without this, would have no chance of working. And like in the real proof, in the proof, we actually will not need the fact, but I will show you the proof why silver adds splitting creoles, because it's sort of instructional for what we will do later. Okay, so at this point, let me erase. Yeah, so most often with these posets, when they, like with random or something, if they do add splitting creoles, then there is a good chance that the splitting creole will be just the generic creole, right? But here, this is a little bit more subtle, because when you are looking at this definition, for example, even if you look at the intervals definition, this does not work here. The generic R, it's just not splitting. Like if it's in some interval, there is no way how it splits, how it could split A. So we'll need to figure out some other way how to create the splitting creoles. And I will do it a little bit more generality than is really needed. So, okay, first I should define what a splitting creel is. So first let me define what a hitting creel is. So let's say that A is hitting creel. So A comes from some larger model, let's say VG. So it's hitting over some smaller model V, if, or let's call it D. Let's say that D is hitting over V if for every A infinite from the smaller model, D intersection A is infinite. So that's hitting. Of because like if we take omega, then omega, like the whole set is always hitting over everything. So that's not an interesting case. But let's say that D is splitting or independent over V if D is hitting. Okay, if D and both D and complement of D are hitting. So this means that if we look at intersection of D and A, it's not only that it's infinite, but also the complement of. So silver adds splitting creoles. How do we create splitting creoles? So let's do this construction. So we have R. R is the silver generic. So to the silver generic, we will assign I R. So this will be an interval partition. And define it this way. Say that the nth interval with respect to R is the set of those i's in omega such that I intersection R is exactly n. So this is just a fancy notation. What does this really mean? So if this is omega and here is the generic creole, so these are the let's say that these are the coordinates when R has number 1 there. All the other places is where R has 0. Then this intervals is just that this is the first one, this is the second interval, this is the third interval, and so on. So it's just basically, it's just this simple thing that we like R are exactly the boundaries between these intervals. Yeah, and then let's choose some K and N. Then we will use this definition that D subscript N superscript K, so D K N of R is exactly the union of those intervals such that I is modulo N equal to K. So what does it mean? Just for example, if I don't know, if N is 2, K is 0, this means take the union of all the even intervals. So it's just like this interval union, and so on. And you can play with this, and you can take N higher, K higher.
In the first definition, do you mean the little I intersect R is a multiple of N?
Just
So every N things you see in R, you I think just intersection. I mean, there are like below I, there are exactly n many elements of R. So
How many points in
yeah,
R?
or just like forget this definition. Just look at the picture. That's much more useful. Just look at it.
It's a real, not a number.
R is a subset of omega.
Yeah.
okay.
Yeah, I mean, this really what is important is this picture. You don't really need to. It's just the picture should be sufficient for what we need. Okay, I claim that this is a splitting creole. So right. For if you have to fill in the quantifiers. Yeah. And yeah, so of course what is it's K is more than n, then what is really necessary to prove that it's hitting? If we prove that it's hitting for every K, the splitting comes for free. So I claim that this is hitting. So how does the how does the proof go. And this is, I will, instead of really like working formally with the conditions and condition, I will try to draw pictures because I'm too lazy to denote it. But I'll try to be consistent with the way how I.
R is your genetic.
Sorry?
R is your genetic.
Yes. So let's suppose that we are given some condition P, and we are given this K and N, and we are given some set A, which is infinite, and we are supposed to make P stronger, such that it forces that there is some intersection between A and this set. So this is omega, and then this is how I will be drawing conditions. So the condition is a function, so at some places it has already 1 written. So let's draw it like this. So these are the places where 1 is written. Then there are some places, okay, the one thing which I didn't say, and I'll be using here with the definition of the silver forcing, I will always assume that the pre-image of 1 is always infinite. So there are infinitely many places where the value is 1. This is a dense subset of the poset, and I'll be always working with this. So yeah, so I've infinitely, this means that there are infinitely many points like this. Then there are infinitely many points which are infinitely many coordinates which are in the complement of the domain. So let this be blue if that's okay. Let this be blue. Maybe red might be better. Yeah, let's make this blue / red / pink. Then how do I how do I work with the condition? Then I can make the condition stronger by either turning some of these colored points into white ones, so just this, so this is like putting there 1, or I can erase them and put there 0, and the result will be a condition as long as I keep infinitely many red points. Okay, so a condition which is which looks like this. I have A, so first I will look for some A in A such that which has below it, so let's say that this is A, and I want below A I want at least n many red points. So A intersection codomain B is at least n. Since A is infinite, there is such n. Yeah. And I mean, yeah, we can assume that the picture looks like this. So then we will try to do 2 things. So first attempt, just in all these red places which are below n, just put there zeros. So just erase all these points. This is a condition because I haven't touched any of these infinitely many red points which are past A. And moreover, the condition P already knows in what will be the index of the interval where A belongs to. So it's just some number, right? So 2 options. So let's say that this version of the condition forces this to be I. Okay, I'm not very inventive with letters, so I have to prepare the names of things in advance. L. Yeah. So either L is already equal to K modulo n, then we are done. Or second option, this is we are not lucky, this did not happen. So then we can compute how far off we were. So what is K minus either K minus L or L minus K, K minus L. Let's see what is K minus L modulo this is that this tells us that we are off by this number. Let's call it S. We are off by S. So we need this. We need the index L to be exactly larger by S. S is definitely smaller than N. So remember again that we in fact erased some red points, at least N red points. So just instead of erasing all of them, just create as many of them into ones and just erase the others. What's the result? Again, the condition knows this index, and moreover we can compare it. We know that it's exactly by this S different than it used to be before. So now we shifted it, or we shifted the indices so that now we are in the proper interval. And yeah, the proof is done.
The complement should also be there.
Sorry?
Well, once we split, we have to split the complement.
No, but it's just a different case.
Yeah.
Yeah, so we proved for, okay, yeah. So for every K we proved that this is hitting. But since these are disjoint, then yeah. Okay. And so sort of the key to the proof is that we can do this manipulation with conditions. That the proof is nothing else than just doing this manipulation so that it fits together. Okay.
So you show there is 1 point, but you can get more because you can go as far right as you want.
Yeah, but I mean the way I define it is that I just want it to be non-empty, right? Which is equivalent.
Well, you showed you said infinite.
Oh, okay, right, okay, yeah.
You showed it for all A's, so it's true for all.
Yeah, let me just claim that I proved it perfectly, and that's, yeah. So this manipulation, this is like the only thing which we will actually need to do. Yeah, so now I will not, first I will prove something sort of technically easier than the silver result, but the key argument is the same, and then time permitting we will see how to modify this to get the silver result. Okay, so proposition, so suppose that U is an ultrafilter, non-principal ultrafilter. And then the omega product, so side-by-side product of omega many silver reals, of silver forcings, forces that U cannot be extended to P point in any further Sachs property extension or with any further Sachs property forcing.
This product is finite support.
It's no, it's countable support. So in this case, it's full support. So we are still using this this definition that we are doing products with countable support.
Sorry.
Let's suppose that yes, you could have the Cohen real.
Oh.
That's
bad.
Yeah. You're exactly right. Yeah. Yeah. And I mean the fact that in any further Sachs property extension, then that's not very important. That will come in free for it will be obvious that this will hold. Okay. So this is not yet the full. The things which I promised you is this, and that's also true. But let's start with this thing. This is sort of technically easier, and the argument is the. Sorry? Yeah. It's somewhat messier, but like this. Yeah.
But this is enough because you take a cutoff anyway.
Yes, yes. Like the only thing for which this is not enough would be like this result. For the other result, this is already sufficient. Like because this V0, this donut ideal, we have it defined for silver. Yeah. Otherwise, yeah, for
This equals omega 2, you need to do this many times, no?
yes, yes. But this is already definable forcing, so I can claim that the result of countable sport iteration of this is canonical model, and yeah. Basically, I could take this as my forcing. Yeah, the only thing for what this is not good enough is this claim. Otherwise, this is already good enough for everything.
Sorry, about the coenreals, does a single coenreal add a viewpoint? I mean, adding a single coenreal, is there necessarily a viewpoint?
In the extension, I would think yes, but I can't prove. I can't. Yeah, like the way coenreals help you is that so we will add some partitions of omega, and the ultrafilter will need to choose which part of this. Always one element of each partition which is adding, and I think the coenreal will help would help, or generally could help choosing this. Right? I don't know. I would need to think about it for a moment.
Like how a single coenreal affects the cardinal characteristics, and I don't know. It also a single one can make D. I don't know. There are results like this. But
okay. Yeah, I would need to think about it, and I guess now is not the time. Okay. So yeah. So let's prove this. So this is just so this adds an omega. This adds omega many silver reals. So let's denote them Rn. Let's say that Rn for n in omega is the silver real added at the nth coordinate, and then we will define D. So this should be somewhat similar to what we use for the splitting creoles. So D and K is, oh, I erased it already. Okay, never mind. It's D of the nth splitting of the nth silver real K, and we just need some index here, so it's something like n plus 1 square plus 1, but this is not very important. Yeah. So remember before, like when we had a real or generic real, and we set this d, k, and some index here. So we looked how we checked how this real is dividing omega into intervals, and we took union of those intervals which such that their index is modulo this thing equal to k. So you'll be doing the same thing. What I wrote here is, I think what is needed is n plus 1 square plus 1, but I mean, it's not very important what this number is. It's just we just want it to be large enough so that at some point we can say that something is big enough. So maybe I'll be just writing n square, and n square is in fact not the right thing, but it's not the.
What is D and K equals? D equals that index K.
Okay.
This is just notation.
Yeah, that's just the notation. Which when we had this proof for adding splitting creoles, so we introduced this notation. So these are the.
Oh, there is no R.
Yeah, it's sort of a little trick, but I mean, yeah. And, these are like not very important things. Okay. So now notice that like if we fix one n, then this d and k, this is a partition of omega into finitely many pieces. So precisely into this number, n square many pieces. So in the extension, so for example, imagine that in the extension we extended U to an ultrafilter. So definitely ultrafilter we needed for each n to add one of these sets. We needed to find one k which we are adding there. So let's say, let's imagine we have x. So x is a name for a function from omega to omega, which tells us which k we picked. So let's say for each n, in fact it's so xn is something in this n square. So this function is like, this is the name for the function which tells us what things are we trying to add to the ultrafilter.
Maybe you could give a name to this supposed P-point U prime or something.
Okay.
We can say dn xn is in U prime.
Okay. I mean U bar. Okay, let's call it U bar.
That's the one with the extension.
Yeah, that's the, yeah.
The dot on top.
It says a bar. The dot is hidden behind the bar.
You can put the underscore or tilde.
Tilde, okay. We don't have tilde. We don't have acute, but okay. So so the point would be to see that this sequence dn xn is the sequence which is witnessing which has no pseudo intersection. What does it mean? We should for every function f from some dominating family, but since the first thing is omega omega bounding, it's enough to check this just for functions which come from the ground model. So for each f, which is in fact in the ground model, we are supposed to find some function a. So the a is from I guess we already erased. No, this is so we are doing this. So for each f, we are supposed to find some increasing function a, which is above f, and we are supposed to find a set in the ultrafilter U, which will be disjoint with what possibly this pseudo intersection of this could be.
This is now the ground model ultrafilter.
Yeah, we are looking for U in. Yeah. Okay. Now, moreover, we have the Sachs property. So this function xn, although we said it's going to n square, in fact, we know we can do better, right? We can. So like the proof would go that we have a condition, and below this condition, we should find a stronger one which forces this stuff about these things. So we can assume that the condition already below which we are working already knows better. The condition can already assume that we have a tunnel, slalom. So we have xn slalom. So that xn has size n plus 1, and the function x is already forced to go through this ground model slalom. So we know even better. So for
xn has size n plus 1, you said it, but you didn't. Right.
Yes.
The size of the tunnel is small.
Yes, I still have it over there.
Oh, okay.
Sorry, I'm just too lazy to write everything down. Okay, so what does this tell us? This tells us that the xn is in fact subset of union of, we just look at these n plus 1 many options. Goes through xn d I n. So now we even got rid of this name of this function from the extension. We just know that it's somewhere in the slalom. So it's enough to work with this. If we are able to do it for this thing, then we are able to do it for this thing. Okay. So in fact we know that like this tells us that what were we doing here? We were sort of tracking on what's on this, when we were looking at it at DI, we were keeping track of what's happening in this interval A. So we don't have the function A, but our goal is to find some function A, so it is something that will work. So we want to control this A. So we know that, or we want to find A such that this sequence Pn xn. So this is definitely a subset of union j goes over omega of, and now we are going through the intervals. So this is subset of this union xn d I n, and just keeping track of it on the interval. So we can just try to work with this set and to find u, which is disjoint with this particular set. So this is just basically like we are keeping track of it, what's happening on the intervals, and on the given interval we know that di is just definitely one of these di's, which or dn is one of these i's for which is in xn. So we just take union of all of them. So this is definitely a superset of what we are trying to control, of this possible pseudo intersection of this p, which, yeah, never mind. And now will come the actual proof, the actual work, what we do. So what's the, we are supposed to find A and U and a condition below some given condition such that we can ensure this thing. So we are given some condition which we are supposed to strengthen. So we have this. So we have omega many coordinates. So let's say this is the first coordinate, this is the second coordinate, and this is the nth coordinate. I will be calling the projection on the nth coordinate P sub index of the coordinate. And so this nth coordinate is adding the Rn. The silver real Rn is added on the nth coordinate. And the condition already knows something. So the condition has on like each on coordinate we have silver conditions, so there are infinitely many ones, and there are definitely infinitely many empty places, or places which are not in the domain of the given Pn. And so on the first coordinate we are computing, like on the nth coordinate we are computing modulo n plus 1 square plus 1, something like that. Okay, so how do we find this function A? So we will do it inductively, like one step by step, always the next value of A. So first we'll find A such that for each n we will pick, so suppose that the function is already defined below n, and now we are defining at n. So we want to find some an which is bigger than fn, and both a n minus 1, like just such a always exists. And moreover we want that when defining an, then when we will be looking at the nth coordinate, so an intersection of codomain of Pn, we want this to be large, let's say n squared. So what does it say? So let's say that we have defined the function below n, and now we are defining the nth value. So we will look at the nth coordinate, and we know that an has to be something higher than fn an, simple enough, and moreover there has to be at least n square many red points below it. But since there are infinitely many, then this could be done, right? So let's say that it's, I don't know, here. And this, so we define function a like this. So let's say that this is a n, and let's say that here we will define a n plus 1 somewhere. So this is the one which we will define in the next step and so on. Okay, and now I claim that this works. Then now we can strengthen the condition such that we can achieve this. So what are we trying to do? We are trying to control what's going on with Rn. So what's going on the nth coordinate in the interval an plus 1 minus an. So on this coordinate, we are trying to control what's happening in this particular interval. Like what's happening elsewhere, just that has no impact on what we are doing. We can do whatever we want. We don't care. The con does not influence what's going on. Okay. So first thing which we'll do for at every coordinate, we will erase all the red points which are in this interval which we are controlling. So just it doesn't matter if you erase them or put there 1. We don't care. We don't want any red points over there. So we can. So let's suppose that we have already a condition which looks like this. Then, okay, first attempt. Put zeros, like instead of all the red points which are on the nth coordinate and are below an, put their zeros. Just erase them, get rid of them, put their zeros. This is legal because we haven't touched the red points which are above an, so there definitely are infinitely many remaining, so this is fine, we have still a condition. So, and what does this condition know? The condition already knows what is the generic interval partition in this given interval. It exactly knows the indices of these intervals. It knows what the intervals are, and it knows exactly what is the index of any given interval. So, okay, yeah. So the condition, this condition which we created, it decides the set, the set union of di. din I comes from xn intersection an plus 1 minus an. So the condition decides exactly what this set is. So let's say that it decides it to be hn. This is just a name, just call this hn. Okay. First option, we were lucky. Union of hns is not in the ultrafilter. This is a ground model set, so we can ask, is it in the ultrafilter or not? Suppose that it's not. Well, then we are done. This set is just this set, right? That's in fact exactly this. It's not in the ultrafilter, so the complement is in the ultrafilter. We are done. Okay, so this is in case we were lucky. Other case we were not lucky. So we need to do something else. So what we do, we remember that how we got this condition, we erased all these red things. So let's put them back. How many we have? Like this n square many. So, and we knew that we were not lucky in the first case. Well, which means that we sort of should do something. So, yeah, this lemma. So we have, let's G be the additive group. G is Z n square, x is xn. We are set up precisely for this lemma. For each n, we are getting this Sn some number. We know that if we shift by Sn, if we shift x by Sn, it's disjoint what we had before. So come back here, and so we had at least n square, or this number of points where we can still put either 0 or 1. So what we'll do, we'll put exactly Sn many 1, so exactly Sn many we will turn into new boundaries between intervals, and we will erase the other ones. So again, the result is again a condition, and again it fully determines what this set is. It fully determines this set, and moreover, since we shifted exactly away from the indices, the intervals which have indices which are modulo, which fall into the right equivalence class, are definitely different than they were before. So now it designs this set, and it decides it to be, it knows that it's disjoint from Hn. What it means, the union, again we take the union, in this case it cannot be in the ultrafilter because this was in the ultrafilter and this was disjoint. That's it, we are done. And yeah, that's the proof of the proposition. Okay, maybe let me just comment on how we, for example, how the big continuum is achieved. So just take kappa, which is a regular cardinal bigger than omega 1, strictly bigger than omega 1, do this countable support product. What does this do? Okay, first maybe I should comment that, before that let me just comment that I didn't argue about the further Sachs property extension, but like what we were using, we are only using that we can trap xn into a slalom, and we were using that the function f, it was somewhere, yeah, the function f comes from the ground model. As long as we have the Sachs property further, then we can still do this exactly the same way, and then the proof is it's just exactly the same thing. Yeah, so this already gives us this canonical model. Just do countable support iteration of these forcings of length omega 2. There are no p-points in the extension. If there were a p-point, there is some reflection argument. It would be a p-point in some intermediate model, and this we forced with this. And well, it will be. We don't even need it to be a p-point in the intermediate model. Just an ultrafilter in some intermediate model, and it's killed. But so that's the answer for the canonical model question.
Also in the product, you use this reflection. So the kappa side product, you reflect this in kappa barless and kappa.
Okay. Let me just go. Let me say the argument. It's not much detail, but a bit more detail.
Yeah.
So how to get continuum to be equal kappa? So choose some suitable kappa. Do the countable support product of size kappa, and claim is in the resulting model there are no p-points. So let's do this by contradiction. So suppose there is an ultrafilter. Then the ultrafilter, it has to contain for each ground model set either the set or its complement. I forgot things. Okay, so we are assuming CH holds in the ground model, which means that this forcing is omega 2 cc. What does it mean? Every anti-chain is of size at most omega 1, which means that every anti-chain lives only at some support of size at most omega 1, because every element of the anti-chain has only countable support. So for every ground model set, some anti-chain decides whether it is in the ultrafilter or outside of the ultrafilter. So there are only omega 1 many sets in the ground model. Each of them has an anti-chain with support of size at most omega 1. So there are at most omega-1 many coordinates in the product which actually influence where the ground model things are. And so do this, take this, like figure out what these omega-1 many coordinates are and just don't consider them. There are definitely some omega many coordinates which are disjoint from what influences the ultrafilter, or ground model sets and the ultrafilter. And then do exactly the same proof, like all this works. The only point where you might be in trouble is here. At some point you were asked the question, is this union of HNs in U or not? And in general you cannot say yes or no, because it's the ultrafilter is in the extension, it's not in the model where you are. But you can strengthen the condition to decide. And the point is that the strengthening of the condition, it does not touch any of these coordinates where you are actually working, because we said that those coordinates do not influence what's happening with ground model reals. So this is a ground model real. We strengthen the condition to decide whether it is in the ultrafilter or not without touching these coordinates. And then we just go on with the proof and everything works as desired. Yeah.
Why is the silver real in this omega part silver over this model? Because the silver forcing is the ground model, but is this true?
Like you are asking whether we cut it, whether the silver forcing, whether the silver reals which we are adding at other coordinates are silver over the. I don't think so. No. No.
Yeah, but don't you need this the argument?
No, the argument takes place in the ground model.
Yeah, you give me a condition and you enlarge, but the enlargement comes in two parts.
Okay, and you use the second to.
Yes, exactly. Yeah, I pulled everything to the ground model. The only place where I actually needed the ultrafilter to be in the ground model in the original argument was here. I had the ground model. I had the ground model set, and I asked a question: is this in the ultrafilter or not? So yeah, this could cause trouble, but we are fine because we can arrange this to be decided without this influencing the arguments we are doing.
So you extend the condition to force the set. What in the ultrafilter, right? In the second part of the. So if it was forced outside, then you're done, right?
Yeah.
If it's okay, so it's going to be forced inside. But when you start changing the condition below, are you still forcing that?
Yeah. So how like done properly what this argument says. So there is a set of coordinates such that of size omega-1, such that whenever I have a condition and a ground model real, and that's name for the name, then okay, let me answer for the others as well. So whenever I have a condition and a name for a ground model real, I can strengthen this condition while changing only the coordinates in this bed set, so that this stronger condition decides whether this ground model real is in the ultrafilter or not. So I'm using it here. I am strengthening the condition which I'm working without changing only the coordinates in the set where I do not work. Yeah.
But in the iteration, this issue is easier, right? You know that the are silver over the place.
I mean, it's easier as long as you.
It's still the silver iteration.
Yeah, I mean, it's easier as long as you don't need to argue that you are using the reflection. You know, there's it depends on what's, if you need to explain the reflection, then I probably prefer explaining this over the reflection argument. Yeah. I guess we are about out of. Well, I'm about out of time. So let me just comment on the other things which I wanted to do. So then there will be the question how to get from this into this, and sort of the argument is the same. We just need to somehow do this all at one coordinate. So this construction had actually one feature. When we were working with the condition, we were always just changing some initial segment. There was always some final segment of these conditions which did not change at all. We didn't need to touch it at all. So what we'll do, we will how to do it on one coordinate. Just stack this argument on one coordinate. So just somehow create figure out an interval partition, and it will be always one interval where we are working with stuff, where we will leave some zero, and we will leave space to adjust, and then there will be one interval where we actually fix what we are looking at, and we are doing this argument. And then
You have to leave in fully many red points. Right?
yes, yeah. So we always, yeah.
Then you don't actually decide what happens.
Yeah, you don't. Yeah. So what we do, we will have this interval partition. Always one is fixed, and there we are actually doing there we are very interested what's happening, and one interval is for working. So we will be careful about always. So now this function will not be something like n square. It will be something like, I don't know, n cube. I don't know, n cube, n to power 4 probably. So we always have. So we'll always have much many red points than we had before, so that we can always first undo what we did before, like undo possibly the shifting which happened before, and also that we have we have much more space, so even that we are not like before we left, like possibly we left there n many red points because we need to keep a condition. So this creates some uncertainty. So we know that we actually do not know whether xn will be exactly xn or possibly xn shifted by 1 or 2 or 3, but not just at most n. So if we have n to power 4 or something, then we can still, even with this set, we can still make sure that we shift it enough so that it's away from itself. Yeah, so that's basically the argument for one silver is just stacking it on top of each other and leaving much more space, and then the computations are sort of you need to be a little bit more careful when doing the computation. It's a little bit, well, it's much more painful to write it down, but the idea is just the same. And then like the proof of this is very much a standard way how to turn the forcing proof into this sort of proof. So there is no other argument than just like going again through the proof for one silver eel and thinking about it in different terms, but the argument is exactly the same. And yeah, maybe one more comment. There is like one more consequence which I didn't define, and so let me just say it quickly. So here we were computing modulo some n square or something in. So then you can ask, was it really necessary? Like, why didn't we for the splitting creoles? It was sufficient to have just this to be just 2 odd evens. And so do we really need n square? And the answer is no, we don't. Like you can do it with 2, and just you need to you then need to be a little bit more subtle when doing this argument, and then actually this lemma will be used for slightly different group. And what does this achieve? This will achieve that in the extension, every ultrafilter will contain a set of size continuum, such that whenever you take an infinite subset of this set, which comes from the ground model, this will not have a pseudo intersection. So this is something. So this is not that there will be one particular sequence of pseudo intersection, but there will be a set of full size, and you take just an infinite set, which comes from the ground, or which is indexed in the ground model, and this will have pseudo intersection. And why this could be interesting? There is this problem about Tukey type of ultrafilters. This is a problem which Stevo and Natasha and Dilip were looking at, and people are looking at. So, so when you have ultrafilter, you can look at it as being a filter means being directed downwards, right? So you can this is a directed order. You can start comparing ultrafilters with the ordering of real inclusion as both sets and comparing them with Tukey order. And for example, P-point is, so there are always ultrafilters which are Tukey equivalent to C to less than omega, so the maximal Tukey type of size continuum. There are always such ultrafilters. And if you have a P-point is Tukey not equivalent to this, P-point is not Tukey equivalent to C to less than omega. But if there are not P-points, then you don't know. So the question is, understand that every ultrafilter is Tukey equivalent to continuum to less than omega. And equivalent formulation, is it consistent that every ultrafilter contain a subset of full size such that any infinite subset has no pseudo intersection. So, so you see the difference between what we proved and what we want is just coming from the ground model. We proved that every ultrafilter has subset of full size such that any infinite subset or any infinite subset indexed in the ground model has no pseudo intersection. And we want to leave out the index in the ground model. And so, this is called Isbell problem. And we don't have answer for that. Yeah, okay, let me enter this problem.
We've already had several questions. If there are any more.
I don't just, what happens if you, on top of this extension, you have further sex extension? Do you know if there's new P-points added or?
Sorry, so you do some of this thing, and then you do something further which has still the Sachs property. You're fine. You have still no. This axiom. I'm not sure about the axiom, but you are not adding any. Okay, but you can introduce some new P-points. Again, I would need to think about it. I'm not completely sure now.
Did you say anything at all about the analog problem for omega P-filters?
Not as far as I know. So this is okay. What Andrea is talking about. So there is again this old problem, which is about whether there always exists a non-meager P filter. And so when you have a filter, you can look at it as a subset of counterspace, and then you can start talking about like being non-meager and so on. Ultrafilter is always non-meager. The equivalent formulation is that enumeration functions of the things in the filter are unbounded. And so P-points are examples of non-meager P filters. And it is not known whether non-meager P filter, the existence of non-meager P filters is a ZFC theorem or not. And again, I think there are some results that like non-existence of non-meager P filters has some consistency strength. It has some strength of some large cardinals, but I don't think this. I do not know how to use this for non-meager P filters.
I thought I waited until you stopped making
I mean, that might be a very long time.
I meant nothing bad. You looked very deep in thought. I'm gonna stop talking now and then. Now no one will ever ask a question.
So do you know for the original Sherach thing, he used omega-omega bounding?
Yes.
If you add on top of this random reals, do you know if it's known whether what happens? I
see. So you're asking first adding some silvers, and on top of that adding random.
No, I mean this Gurdjieff product from Sherach.
Like generally, if I have model without P-points and I add some randoms, what happens with? Obviously, the answer is that I don't know. I probably can't even figure it out right.
How do you know anything about adding randoms other than if either you first added coin or square holes? But anything else, any other question you can come up with is a mystery.
Okay, well, since you asked this, I'm tempted to add like one more comment about what this has done. So this, as you mentioned, the Shelach proof is done by Grigoriev. So it's roughly that you are given a P-point and you plug it into Grigoriev forcing, and this prevents this ultrafilter being extendable to a P-point. this could seem similar, because what is Siller forcing? Siller forcing is first you force this p omega modulo finite, and after that, so this adds a selective ultrafilter, and then you do Grigoriev with this particular selective ultrafilter. So, for example, this Siller iteration is just alternate between adding selective ultrafilters and forcing with Grigoriev with them. So in some sense, it looks very similar to what Schellach did. But the core of the argument is actually what, so again, Schellach.
So Siller forcing adds an ultrafilter, a Ramsey ultrafilter over the ground model?
Yeah, and then it, and
destroys it,
yes.
No, but over the ground model, it's
yes, yes. Yeah. So Schellach's argument is that plug P point into Grigoriev, this will kill the P point. This argument says something very different. It says take Grigoriev, plug in a selective, it kills every ultrafilter which is not near coherent with the selective which you plugged in. So this says you are killing like exactly the other ultrafilters than the one which you plugged in. Grigoriev, the Schellach's argument said you are killing the one which you are plugging in, which you plugged in.
I mean, the Schellach proof actually was not a countable support iteration, but it actually started. There was no coming. Weber just had published this paper, and there was no properness around. And I think it was first doing sigma closed forcing to add a generic CCC forcing, which controls the ultrafilters. And the CCC forcing doesn't only take care of all P points, but of all P filters. So that was something, which is
yes,
different from what we do now.
Yeah, and yeah. So in some sense, at least, technically it was different, and I actually never managed to read through the.
Probably the same.
I think this original argument for no P points, it was sort of morally the same as the thing which originally Schellach did with the Grigorievs. So because the CCC forcing which he used are like sort of CCC'd version of Grigoriev, but I don't understand it this method fully, so I can't make any more claims about it.
No, I have one.
Why not?
So just about diamond R. So do you have any tendency, do you suspect the diamond is necessary, or
for the diamond R thing? That good question would. So you're asking.
are sufficient to get the people?
I don't think so. And this is actually okay. There was this paper of Schellach 980, which has been around for like 10 years, and nobody ever understood it because it was never correct. And this was. I mean, it sounds like a joke, but there are several versions of it, and this was what Martin and Diego were trying to work on. So this was okay. So there is a question: does U U equal omega 1 imply the existence of P points, or like is there a way how to basically there is very much interplay that manipulating U is very much like the only methods known for manipulating U is from actually manipulating P points. So basically this is the question: can you increase is there some preservation theorem for ultrafilters which are not P points? So this is very much connected to this.
So that this paper there are n versions, and so far n of them don't work, but there will be an n plus 1 version. So.
Really? Okay. I sort of thought that you gave up already. Yeah. So that's. I think it's suspected that this is not the case, but the paper is not correct yet.
Are there any other questions?